Ever stop to think about all the hidden chemistry that's happening around you, like right now? There's this powerful, invisible force at play in everything from the food you eat to the stuff under your sink. Today, we're pulling back the curtain on the world of acids and bases. On one hand, this force is exactly what's responsible for that sharp, mouth-puckering sourness you get from a lemon. It's a taste we all know instantly, right? A key part of so many foods we love. But then, on the flip side, that exact same chemical principle is what makes drain cleaner so powerful that it can just obliterate tough clogs. So, sour candy and industrial-strength cleaners, what on earth could they possibly have in common? Well, this powerful, super reactive principle happens to be one of the most fundamental concepts in all of chemistry. It's shaping the world around us in ways we almost never notice, even when it's just doing its job inside our pipes. So what is this mysterious force that can be both delicious and, well, a little bit dangerous? What's the hidden link between the battery in your car and the acid in your own stomach? The answer is acids and bases. Think of them as two sides of the same chemical coin, this fundamental duo that runs countless reactions all around us. So let's break down what they are and, more importantly, how they actually work. All right, first step, let's explore the world of acids. You've definitely heard the word, but what really truly makes something an acid? It's a lot more than just having a sour taste. Okay, so scientifically speaking, an acid is any substance that produces hydrogen ions when you dissolve it in water. These tiny little H+ ions then grab onto water molecules and they form something called hydronium ions. All you really need to remember is this: the more hydronium ions you've got, the more acidic the solution is. Simple as that. Now, those hydronium ions are what give acids some really distinct properties. We've already talked about the sour taste, but they are also corrosive. That's what lets a strong acid literally eat away at metals, which is super useful for things like cleaning steel. They also have this very specific reaction with compounds called indicators, and we'll definitely be coming back to that. And trust me, you see these acids everywhere. Acetic acid, that's just a fancy name for vinegar. The hydrochloric acid in your stomach, yep, that's what helps you digest your food. Ascorbic acid is just plain old vitamin C. And that powerful sulfuric acid is what helps get your car started every single morning. Now, for every acid, there is an opposite, a base. If acids are one side of that chemical coin we mentioned, bases are the other, and they come with their own totally unique set of properties and uses. You can define a base in a couple of ways. First, it's a substance that produces hydroxide ions, that's the OH- part, when it's in water. But there's a broader definition. A base is anything that can accept one of those hydrogen ions from an acid. They're kind of like natural chemical partners. Their properties are a huge contrast to acids. Instead of sour, they taste bitter, and they often feel slippery to the touch. That's not a coincidence, by the way. That slippery feeling is the base literally reacting with the oils on your skin to make a tiny bit of soap. But you gotta be careful, because just like strong acids, strong bases are also super corrosive. And their applications are just as common. Sodium hydroxide, also known as lye, is the absolute powerhouse in drain cleaners because it's just amazing at dissolving grease and hair. Ammonia is a classic household cleaner. And hey, if you've ever had heartburn and taken an antacid, you've used a base like magnesium hydroxide to neutralize all that extra stomach acid. So we know what they are, but how do they actually do what they do? To really see that, we have to look at what happens when they meet the most important solvent on the planet, water. This is where the chemistry really comes alive. See, when you put an acid or a base into water, they don't just float around. They go through this really fundamental change that completely unleashes their power. Acids go through a process we call ionization. So for example, when hydrochloric acid, or HCl, hits water, that acid molecule basically splits apart. It donates its hydrogen ion to a nearby water molecule, and boom, that's how you create the hydronium ion we were talking about earlier. Bases do something just a little bit different. A lot of them, like sodium hydroxide or NaOH, they just dissociate. That's really just a fancy way of saying they break apart. The water pulls the existing molecule into two pieces, releasing the sodium ion and the hydroxide ion that were already there. It's less about creating something new and more about releasing what's already inside. And you can see the key difference right here. On the left, you've got the acid, which has to create a new ion by reacting with water.
On the right, the base simply releases a hydroxide ion that it already had. It's two different paths to get to a chemically active solution.
Okay, but wait a second. What about ammonia? We saw it on that chart of bases, but if you look at its formula, NH3, there's no OH in there to release. So how can it possibly be a base? Ah, and this is where that second definition of a base comes into play. Ammonia works by actually accepting a hydrogen ion from a water molecule. It basically plucks an H plus right off of an H2O molecule. And when that happens, the ammonia turns into an ammonium ion. And what's left behind? You guessed it, a hydroxide ion. It's a really clever way to get the same result. So now that we get the deep chemistry, let's circle back to the original question. In a lab, if you can't taste or touch something, how do you actually tell if a solution is an acid or a base? The answer is something called an indicator. This is a special compound. You've probably seen classic litmus paper that's literally designed to change color depending on whether it's in an acidic or a basic environment. It's a super simple visual test that lets us see that invisible chemistry at work. At the end of the day, acids and bases aren't just some abstract concepts from a chemistry textbook. They're this fundamental pair of opposites, a kind of yin and yang that makes our food, our technology, and even our own bodies function. And it really makes you wonder, right? What other incredible invisible forces are hiding all around us, just waiting to be explained?